Okay, so now in case of oblique impact, now we will extend the relationships that we develop for central impact to the case where the initial and final velocities are not parallel. So as you can see in this case, we will consider a situation that if you consider two particles, particle 1 and this is particle 2, and the mass of this particle is m1 and the mass of this particle is m2, and during the impact these will come in this direction and this will obviously come in this direction here, and then these particles will collide with each other and then it will go in this direction here, and this particle will go in this direction here. Again, this is m1 and m1, and this is m2 and this is m2 here. Now the center of gravity of this particle is here, the center of gravity of this particle is here. So again, if you draw a line here joining the center of gravities, so this line is what we call is the line of impact. And we can also draw now another line which will be passing through the contact point between the two particles and which will be perpendicular to the line of impact, and this line is what we call is now the plane of impact. Okay, so now as you can see the mass m1 is going with the velocity v1 here, and we can see that the velocity is not in the direction of the line of impact, it's making some angle with it. So this is our plane of impact, and maybe the velocity can either be represented with the line of impact or the plane of impact. So let the initial velocity here is theta 1 for mass m1, and similarly the velocity of particle 2 before impact is v2, and the angle that this velocity is making with the plane of impact is theta 2 here. So we have particle 1 and particle 2, and the velocity v1 and v2 are the velocities of these particles before impact, and theta 1 and theta 2 are their directions. Now after impact, which is this point here, the particle 1 will go in this direction, so we can say that this will be the velocity of this particle 1, and we will represent this by v1 dash. And similarly, the velocity of particle 2 will be in this direction, and we will represent this by v2 dash here. Okay, now instead of uh, in this plane of impact and line of impact, we will represent these by tangential direction here. We will call this is a t, and we will call this is n. So this is normal direction and this is tangential direction. So tangential direction is it's passing through the contact point between the two particles here. And in addition to these velocities, we also now have angles with which these velocities are going, and these can be measured with respect to the t direction here. So we will call this theta 1 dash, which is this angle here, and you will also have theta 2 dash, which is going to be this angle here. So now this is the situation of oblique impulse, oblique impact here. So in this case, you may be given m1 and m2 and v1 and v2, and you will be asked to calculate the final velocities after impact, which is v1 dash and v2 dash, and again you will also need to calculate their directions. So in this case now there are four unknowns, so we need four equations to solve the problem of oblique impact, and therefore it's relatively complicated as compared to the central impact. So now here, a spherical particle of mass m1 and m2 have initial velocities v1 and v2, as you can see in this figure here, in the same plane of and approach each other on a collision course. So which is the bodies will collide here. The direction of velocities, velocity vectors are measured from the direction tangent to the contacting surface here. So this is the tangent, and the directions in this case are measured with respect to this t here. So this is theta 1, theta 2, and this is theta 1 dash and theta 2 dash. Now, thus the initial velocity component along the t and n axis are. So because normally you will be given theta 1 and theta 2 and v1 and v2. So here we can calculate the component of this v1 and v2 in the n and t direction. So in the n direction here, so as you can see, this will have two components. So one is in this direction and another one will be in this direction here. So this will be v1 t, and this one will be v1 n. This will be t, and this will be n. Similarly, v2 will have two components, one in this direction and one in this direction here. And this will be v2 in the t direction, and this will be v2 in the n direction here. So and obviously if this is angle theta 2, so this will be also theta 2 here. So now we can write this this v1n and v1t. So v1 in the normal direction, which is the component of this velocity in the normal direction. And as you can see, the n is positive here, and v1n is in the opposite to the n direction, so it will be a negative. So you can call this is minus v1, and this will be sine theta 1 here. And then you have v1t. So v1t is the component of this velocity v1 in the t direction, and this is v1 cos theta 1 here. So v1 t is v1 cos theta 1 here. And as you can see, this this v1t is in this direction here, so which is in the positive t direction, therefore it's positive here. Okay, and now in addition to this, we can also write the component of the v2. So obviously v2 have two components. One is v2n. So the normal component of this this v2, and again normal component here is in the upward direction, which is positive, because the this is our n here. So v2n will in this case will be v2 sine theta 2 here, and in this case v2t is again the tangential component of this v2, which is in the t direction, and this will be just cos theta 2. Okay, now in case of this specific case, which is the oblique impact, as you can see here, you have these are our two balls here, or two particles, which are colliding with each other, and this is their n direction. So in this case, the contact force will be only in this normal direction. So this is our F here. So it's really very important to know that the contact force in oblique impact is always in the n direction. In t direction, so there is no contact force. This is very important statement that you should know, that in case of oblique impact, the contact force is only acting in the n direction, and in the t direction there is no contact force. And this statement is very important to derive the equations for the oblique impact. And obviously we know that the way this force will vary or will change during the time. We saw this figure below before. So if you call this diagram here, so the way it was changing was going to maximum on this point here, and then it was going to minimum. So this is 0, and this is t naught, and this is t. And from here, from 0 to t naught, it was fd, and then from t naught to t, it was fr. Okay, so the impact forces are F and minus F, which is these forces here, vary from 0 to their peak value during the deformation period, which is this is our FD here, and FR is the restoration force here, back again to 0 during the restoration period, and T is the duration of the impact interval, so from 0 to T. Okay, so now for a given initial condition of M1, M2, V1N, V1T, V2N, and V2T. So if you are given all these quantities here, there will be 4 unknowns, which is V1 dash N, V1 dash T. So you will need to calculate the tangential and normal component of the velocity for particle 1. And similarly, you will need to calculate these 2 components for the velocity of particle 2 after impact. And the 4 needed equations are then obtained as follow. So first we will consider that the momentum of a system is conserved in the n direction, because in n direction you have this force, which is the contact force, but we know that that F and minus F are equal and opposite. So these will cancel each other, and therefore for the whole system we will be able to write the law of conservation of momentum. But it's very important to know that this equation is only applicable in n direction. It's not applicable in t direction here. So if we are writing this equation, it's only in n direction. So if we are writing the equation in n direction, so we will consider only the velocities which are in the n direction. So as you can see in this case here, that g1 and should be equal to g2. So this means that the g1, which is the linear momentum of the system, which is 2 particles before impact, equal to the momentum of the system of the 2 particles after impact. So but this will be in n direction here, so it's important to realize that it's in n direction only. So what we will write that m1 v1 and this will be v1n here, and then m2 v2n, so equal to m1 v1 dash n and plus m2 v2 dash n. So we can write this equation, which is the law of conservation of momentum for the whole system. So this is the linear momentum of the system in n direction before impact, and this is after impact here. Okay, now in addition to this equation, because there are 4 unknowns, so we need 3 more equations to calculate all the 4 unknowns here. Now, because in t direction, as we discussed earlier, that there is no contact force in t direction, so the momentum of each particle is conserved in the t direction, since there is no impulse on either particle in the t direction. Because in t direction there is no force, so therefore the impulse of that particle will conserve in that in the t direction for each particle. So what we can write here, that m1 v1 t should be equal to m1 v1 dash t. This is the momentum of the particle 1 before impact, and this is momentum of the same particle after impact, but it's in the t direction. So because there is no contact force in the t direction, so the momentum of the particle will remain the same. Similarly, we can write the similar equation for particle 2, so which will be m2 v2t, and this will be equal to m2 v2 dash v2 dash t. So again, we can write a similar equation for the particle 2. So that is the momentum of the particle 2 will conserve in the t direction. Now, so far we have three equations, but now we need another equation for because we have four unknown. So another equation will comes from the coefficient of restitution. So as in the case of central impact, the coefficient of restitution is a positive ratio of the recovery impulse to the deformation impulse, and we derived equation for the coefficient of restitution in the previous case. So which was just E was equal to V2 dash minus V1 dash divided by V1 minus V2. This was the equation that we derived previously. But now in case of oblique impact, because the contact force only acting in the normal direction, and we were deriving this equation for the previous case for the central impact. So we take into account the contact forces, and because this is just the ratio between the restoration impulse and deformation impulse, so therefore this means that the E for oblique impact will be only in the n direction here. So this means that you will have to write n here. This means that this is the equation of E for oblique impact. Now you have four equations and four unknowns. You can calculate these four unknowns here. So once the four final velocities components are found, the angles theta 1 dash and theta 2 dash may be easily determined, which is straightforward to calculate. Okay, so this is the end of today's lecture. We will just summarize that in today's lecture we discussed about impact only. We discussed two type of impact. One was oblique impact, and one was central impact. So this is the diagram for the central impact. That is, the velocities are in the direction of the line of impact, and in the oblique impact, the velocities are at some angle to the line of impact here. Okay, and then we for the central impact, we discussed that the contact forces are equal and opposite during the impact, and the linear momentum of the system remain unchanged. So then for this specific case, we were able to write this equation, that m1 v1, which is the momentum of particle 1 before impact plus momentum of particle 2 before impact, equal to the momentum of particle 1 after impact and momentum of particle 2 after impact. And because in this case there were two unknowns, so we needed another equation which we derived by using the coefficient of restitution. So the coefficient of restitution is the ratio of magnitude of the restoration impulse to the magnitude of deformation impulse, which you can write in this form here. So this is the restoration impulse and this is the deformation impulse, and this is the diagram that you can write here. And finally we derive this equation, and in this equation for the coefficient of restitution, which was the relative velocity of separation or relative velocity after impact, and this is the relative velocity before impact, which you can call is the relative velocity of approach. And finally for in case of oblique impact, as you can see in this figure here, that you have now velocities are at some angle to the line of impact. And here we introduced n and t direction. So t is in the direction which is tangent to the point of contact here. And these velocities v1 and v2 are the velocities of particle 1 and 2 before impact. And now these velocity are making some angles. So you may be given the m1, m2, and theta 1, theta 2, and v1 and v2. And you will be asked to calculate v1 dash and v2 dash and their angles. This means that for this case, we need, there are 4 unknowns. So you need 4 equations. So the first equation that we derive is based on this figure here. Now, as you can see, in case of oblique impact, it's really important to know that the contact force will only be in the n direction. There is no contact force in the t direction. So we can write one equation for the whole system, which is 2 particles in this case. So that is the initial momentum, which is of the 2 particles in the n direction, is equal to the final momentum of the 2 particles after impact, and this is in the n direction. And similarly, then we can write the coefficient of restitution in the n direction. So again, this is the relative velocity of separation and the relative velocity of approach. And because there is no contact force in the t direction, so we can also write that the momentum of each particle will conserve in the t direction. So m1 v1 t equal m1 v1 dash t, and similarly m2 v2 t equal m2 v2 dash t. So this is the momentum of a particle before impact and after impact, and before impact of particle 2, and the momentum of the particle after impact. So we have now 4 equations, and there are 4 unknowns. So the 4 unknowns are v1 dash n, v2 dash n, and then v1 t, v1 dash t, and v2 dash t. So if you manage to calculate the component of these velocities, you will be able to calculate their angles very straightforwardly.